I think today it's going to be a very interesting talk with Ugo Bardi. As you can see, he's there.
So very nice to be here. I guess you have to say something, Roberto, and then we start. You tell me when you want me to start.
Okay, fantastic. So as usual, first thing I want to do is to make people remember of what's happening next. So today we're going to have Ugo Bardi. It's going to be about the limits to growth and looking at models. But next week, very important, we're going to have the co-president of the Club of Rome, Florence, coming from a completely different background. She was a manager at the World Bank. When she was very young, she was an apartheid activist in South Africa. So she did a huge career, and I'm very, very interested also in looking more about what she's going to tell us. Then there's going to be myself speaking a bit about my model on finance and energy. And then we have at the end Jayati Ghosh, development economist, looking at the full picture of the Earth for All book, trying to give a basically conclude, let's say, the seminar series. This is the team. So you remember Jorgen Randers on the left. He came for the first presentation and the first Monday. Now everything is online. So if people want to have a look, everything is there. Donella is also known to be one of the main people. Dennis Meadows. They were really the three that led these limits to growth concepts. However, limits to growth also had a lot of criticisms. And it is fine to criticize limits to growth because there were big fallacies there as well, both if you believe in it, also we don't believe in it. So it's good to criticize and build up on it. So, for example, Ugo is one of those who try to look at some of the fallacies and try to go beyond that, right? So some criticism included like the use of technology in the model, how you use data, and that was, I think, the presentation last week. We spoke a little about that. Too complex, or other things like distributional issues. And again, Gaia spoke about that in the second seminar. There wasn't a green energy in 2 weeks with my presentation. And then two things that Ugo looked at quite a lot were the lack of proper representation of the mineral sector and the recycling sector. So that was one thing that Ugo ended up doing a lot of work on. And even think like there's the collapse of the world because food, and then there is no fishery, so there is no the sea world, which is also something quite obvious to say we should expand the model there. And then a number of things turn out now to be different. Climate change, they even know about climate change in 1970. What they were calling that thing pollution. There were things like banning toxic chemicals around the world. There were nuclear, they were expected to grow exponentially. And after the big collapse in 1986 of Chernobyl, they start leveling off. And then, finance and other things. So basically, let's say we are going to cover a bit of these parts in the next presentation as well. So looking first at the work of Ugo. So this one is one of the latest books that Ugo co-authored. It's called The Empty Sea with a colleague called Ilaria Perissi, that she's in Cambridge as well at the moment. So if you have to finish this sentence, how do you finish that? So give a fish to a man and you will feed him for 1 day. Teach him how to fish. And
there's a Chinese saying.
It's basically Confucius, isn't it? And what happened then? He will deplete the ocean, of course, So I took that from Ugo. He gave me a presentation a few years ago. I love that. It was so cute. Other thing he did, again, as I said, the criticism was the model was quite complex. Limits to growth makes you crazy going up the clouds, So he focused a lot on making this simpler. So the limits to growth revisited was a way to go in the mind-sized models, making things simpler, but still keeping the concept. So it was 2011. Then he kept building on that with Extracted. So that's a very famous book of the Club of Rome as well. And then one of the book that is basically, he's the lead author actually of one of these two main books we are presenting with these days, which is Limits and Beyond. It's a huge wealth of knowledge on the limits and limits to growth concept. Another thing to mention about Ugo, and very simply, he is running this blog. So if you're interested in hearing about Ugo, you can find the key concept here. And the blog is called Seneca Effect. And the main, let's say, concept is trying to demonstrate is why growth often goes slowly, and then when you collapse, it goes so quickly, all of a sudden you collapse the entire system. So if you are interested, probably Ugo will speak a little about this as well.
A little. Let me show you something.
Okay, so I'll fantastic. Thank you, Ugo. So again, there is not much to present about Ugo in the sense that his name is already, you know, echoes in these rooms, and everybody knows about him already. So much research going on these limits of growth concepts, and he had been as well president of the Club of Rome in the past. So this is Ugo. I think I spoke already too much, Ugo. So I think at this point I will simply leave you, taking the lead on this presentation. So thank you so much for being here with us.
What I prepared today was such a nice introduction by Roberto. I think you realize that in order to discuss all the elements of this study, which of course we have the 50th anniversary right now, and we could take a few days of discussions. And as you saw also, we wrote, myself with other co-authors, there are several meta books in the sense that there are books about a book, which I can show you to you. This is the book. Okay, I have it. And
Okay.
This is an original copy of the book that was shown, that was published in 1972. And just for your curiosity, this is the Italian version of the book, which I read when I was kind of young at that time. All right, so I tried to spend some time trying to explain the gears that make this study work, what is under the hood, underneath. I'm sorry that some of you are experts in system dynamics modeling, including Roberto, but I'll try to explain also to those of you who are not. So to explain, what is this book about? How does it work? Why some models provide certain results as much as possible, because it's a long, long story. So what happened in 1972 is that the book came out with this graph that you can see here. You see this graph, which is also in color on the front cover of the Italian version. Now, let me try to explain you what is this graph about. So there is a graph here. This is time. And in the case of the limits to growth, we're discussing as a time range of about 100 years. And there are some elements in this graph which there are different scales, but let's call it Q for quantity. Quantity of something. And the first thing is an element that we call resources, natural resources, which goes like this. These are the resources. This is very general. I'll show you a few things. Let's say discussing here about the whole global economic system. And it goes down not linearly, but doing a curve like this. Then there is another quantity, which we call, goes like this. And we call it capital, which may be industrial capital. Could be agricultural capital. You see in the original, there were two capital curves, one for agriculture, the other is renewable capital, and the other is no renewable capital. But it goes like this. And then there is a third curve, also like this, which is called pollution. This is the essential result of the limits to growth. It is the way it works. And the essential thing of this is that these curves are very general. You can see here. It is bell-shaped curve, which is also called the Hubbard curve. Let's call it like this. There are various names for it. So there are a lot of versions, like I have it here. I know I am a little bit involved in this kind of thing. I took it personally, as you can see. Now, the point I would like to make in a few minutes is, why this? That's fundamental point. What happened, and Roberto mentioned the point that the book was criticized, was demonized, was rejected, was ignored, all kinds of things, but because people could not understand why. Why this? And this is so typical when you have something not new, because this is the way the universe works. I will show you that, but new in the sense that people had not been thinking about that. So this is, what is this? It cannot work. Why? And I'll show you how and why this thing can be made to work, but it takes a little while. First, can you think of something that we know that works like that? Some example of this thing that goes bump. You could have more of this. Okay, you see. What does it remind to you? Roberto, can you make an example?
Society like Roman Empire or different society.
Yeah, basically you saved yourself. It's because it is very general. No, this is very typical. It's a trophic chain. Some of those of you who are biologists will recognize 1, 2, 3. So you start, say, from killer whales, big fish, small fish, crustaceans, plankton, and then it's over. But several stages. So it's the way a biological system, an ecosystem works, through a trophic chain. And eventually, it is physics. Physics. It is nothing on this planet can work if it does not satisfy the laws of physics. And when you start dealing with this kind of system, then you discover that there are a couple of laws which count. One is the dispersion of energy, the fact that everything moves according to thermodynamic potential. So it tries to go down the potential levels, like fish eat. Big fish eat smaller fish because they use the metabolic energy of the smaller fish to make the metabolic energy of the bigger fish work. And it is physics, yes, but it is a new kind of physics. Let me be clear on this point. Physics is something that starts with Newton, and Newton starts with an apple. So we could say that physics started with an apple. The original idea of physics was an apple falling, modern physics falling from a tree. It's true, it's not a legend. Newton himself discussed that in his diary. I said, I was thinking of something and I saw an apple falling from a tree. And then he thought of his universal gravitational law, which is very nice, but an apple doesn't have this behavior. That has been a very big problem that we have experienced over the past 200 years, because physicists would like to have an equation for the falling of an apple. And that's not so difficult. I mean, not to say that Newton was a big advance in science, but you know that for a falling apple, you have an equation. A simple equation tells you how a single apple falls. And that's very general. If you want to be more to the point, you say that an apple falls from a tree because the apple wants to utilize or disperse the gravitational potential it has, because it is a certain height, goes down, bumps on the head of Newton, not really, but maybe, who knows, and then it creates a little bit of heat, which is dispersed in the universe, and that's the increase in entropy, and that's the way it works. All potentials have this behavior. I can show you another energy potential. Well, now I'll show you why I use this kind of thing to show you. This is a mechanical potential. And this is loaded. I'm taking a risk for you. It's even though I'm not very dangerous for a human being, I'll show you the experiments we made with mouse traps, and it was painful at times. Ilaria can tell you about that. The problem is that you dispersed mechanical energy, chemical energy, electric energy, gravitational energy, anything you like, but you don't see this as long as you have a single trap, because this is the way the universe works. As long as you have one element of your system, very simple, then it will not show you this trophic chains. You have to have a network. And now that's the key of the whole story. When you have a potential energy which is dispersed through a network, you know, to links and nodes, then you can have this kind of behavior. You can have a trophic chain. Just to make you another example, let me show you something that has a nonlinear behavior. You know, this is a hourglass, and you probably know the story of how we have a hourglass paradigm developed by the Danish physicist Per Bak, and we have this model of the glass falling on forming that pile at the bottom of the hourglass, which has a nonlinear behavior, which looks, under some respect, like the one I showed to you on the whiteboard, because the sand particles, the grains, they interact with each other, so they form a network, so the behavior becomes complex. And that's what makes a sand glass more interesting than an apple, if you are a physicist who is interested in complex systems and not in gravitational physics or space physics or whatever. Okay, so the task I have now is to show you how the presence of a network to dispersed energy can create this kind of effects. And for this, I took as an inspiration another book. I'm showing you a lot of books. I hope this one is in Italian again. It was published in 1957 by Walt Disney, with the idea of explaining to people how nuclear energy works. In 1957, everybody wanted nuclear energy. It was, you know the story, energy too cheap to meter. Energy will be cheap. We go to the moon, or we go to conquer the galaxy and things like that. So that was an incredibly good job they did, because really it explains. I mean, in my mind, after some career in chemistry, I still think of atoms according to the illustrations of this book. You know that a uranium atom can undergo fission, split in two when it is hit by a neutron, and release nuclear energy. Same story. Energy potential, entropy, you go in a certain, goes in a certain direction. One atom of uranium doesn't do anything special. You continuously have uranium all over on this planet, and all the time, here and there, a uranium atom may split, undergo fission. The problem, the interesting part is when you have a chain reaction. One atom emits 2 neutrons, 4 neutrons, 8 neutrons, 16, 32, 64, 128, and so on. And how did Disney explain this to people? Through the experiments of the mousetrap. Mousetraps loaded with table tennis balls. There is a nice movie you can find on the web about this experiment. The point is that they took mousetraps like this, loaded them with balls like this, and I could let this thing go. Let me see if I can do this without killing myself. Release of potential energy. You see, it's not really a nuclear explosion, but it will not create an explosion unless you have many traps. And we start with a nuclear explosion. Ilaria is my co-worker. She's in Cambridge now, and together with Ilaria, we created a simulation of a nuclear weapon seen using 50 mouse traps, each one loaded with 2 balls. Anyway, here is the experiment.
Ready? 1, 2. Done.
When Ilaria says done is absolutely wonderful. Okay, that just to tell you that we did something reasonably serious. We published the results of the experiment. These experiments was actually invented in 1947, but up to now, 70 years later almost, nobody had worried about making measurements. Everybody say it's a fun way to show how a nuclear reaction works. But now we did it. We made for the first time in the world an actual measurements, and we used a mathematical model to analyze the results, and then we published it in a peer-reviewed journal. And it was not so easy because the reviewers you publish about mousetraps in a physics journal, but then they understood. Okay, so what we do with this idea is simply what I was saying. It is a network of uranium atoms which interact with each other with the help of mousetraps. It moves because balls move from one trap to another. And then you have the same, something very similar. These are the curves for the nuclear explosion on the top left, and then the measurements and the fitting for a system dynamics model for the mousetrap experiment. It was a lot of fun. Also, we had some problems with our fingers because it was, try that if you like, but setting up 50 mousetraps and not having one snap by mistake, it is very difficult, but we did it. The behavior is typical that I was showing to you. It's very general. You have one curve for the resources, which in this case are the loaded traps, and one curve for the capital, which in this case is the flying balls. The system disperses energy from traps to mousetrap and then eventually to the environment as low temperature heat. It is physics. And it is very general, very general. The same models work for a lot of systems. It is a new kind of physics which works for complex systems. It's something that we are discovering now. It's not yet completely accepted, but it was developed for the first time by the people who published the first study, The Limits to Growth, in 1972, because they had it in their hands. But it was known before. That's, I think, the start of this idea was the Hubbard model. Hubbard model, you may have heard of it, is the story of peak oil, which by now is a little bit out of fashion, but it's still interesting. And back in 1956, he had this intuition. It was not using models. He was just thinking by comparing with historical data. He found that, okay, in my opinion, the curve of production of oil, crude oil in the United States should follow this bell-shaped curve. It was the first time that the bell-shaped curve entered the consciousness, so to say, of scientists. But it came from a geologist, not from a physicist, but that was the idea. And this test turned out to be reasonably good because production in the United States did follow a similar path. That's again the bell-shaped curve, which is impressive here. how good it is. And this shows how coal production in all European, but also Japan, or other, there are many others. Also here we have Japan, we can have France and others. They follow this bell-shaped curve, which is the way the system goes, the way the system follows its path toward the maximization of entropy. This is an economic system, but still it has to obey the laws of physics. And that's what you do. Then a financial system, because the extraction of coal or of oil is governed by financial factors, but the financial factors are governed by price factors, and the prices depend on availability. And then the availability has a cost, and this is physics. So what you do here is look at the blue points, this red curve, it's England, UK to be more exact. Actually, most of the wells are in the coal mines, most are in England. You start going up because you have a positive feedback, just like a nuclear chain reaction. You start with a mine, the mine gives you the profits to start a second mine. Then you have the profit to start 4 more mines and more mines and more mines. So as long as it is inexpensive to extract coal and you have good profits, you keep growing in a curve which is approximately exponential. This is the same for oil, as you can see, and other examples, like in epidemics. Also, you have this little thing which has been very popular during the past 2 years, but it follows the bell-shaped curve. This is an epidemiological model, which is exactly the same equations that work for the nuclear weapon or for the mousetrap experiment or for the coal extraction story, which shows that just like gravity acts on apples, people, planes, cats, mice, and whatever, the same laws of physics, which we express in terms of system dynamics model, they work on socio-economical systems, also on whales. Roberto was mentioning the story that we published this with the book that Roberto was showing, the empty sea, and that's the way, as you can see, how you empty the sea. In this case, of whales. These kind of whales were called the right whales because they were easy to catch. So you had this curve, but as you catch whales, you run out gradually of whales. You have to go farther away to get the whales. You have to search for whales for a longer time. Catching whales becomes more expensive, and as it becomes more expensive, you catch a smaller number of whales. And so you go through this curve, which is another case of the bell-shaped curve. Eventually here you may be interested to know that at the end of this cycle of fishing or whale hunting, because whales are not fish, but anyway, makes little difference. We started with several 100,000 whales of this particular species at the beginning, and at the end, according to the estimates by people experts in this field, there were some 50 or 60 females of this species left in the oceans, from a few 100,000 to 60, which is remarkable in terms of running out or something like that. So it is very typical, very, very typical. You can have your time, and it's a fantastic field. When you start understanding how these systems disperse their energy, you can play games of all kinds, like we did with our traps. But just to tell you something about the Seneca effect, and we call it the Seneca effect because it's a sentence that was said by Seneca, the Roman philosopher Seneca, back in the 1st century. And he said this sentence: increases are sluggish growth, but the way to ruin is rapid, and which was easy to express. He didn't have mathematical models, Seneca, but it was logic. It made a lot of sense. And then if you look carefully at the curves that I was showing to you at the beginning, you see that they have the Seneca shape. So they go down faster than they go up. And why does it happen? As you can see also, this is the 2004 edition. We call this House of Cards effect. House of Cards of effect, as you know, it takes a lot of time to build a house of cards. Then you just touch it and then it goes down. And for instance, here it could be the number of cards in the castle could go like this, go up to here, and then goes down. And this is a dynamic effect. We have models that can reproduce this effect. Essentially, for your knowledge, the system is a little bit more complex than the very simple one when you have predator and the prey, when you have whalers and whales, very simple. Whales, whalers, you have two entities chasing each other, and then you have the normal, the regular, the bell-shaped, symmetric bell-shaped curve. When you have a third element, which may be pollution, as I was showing you at the beginning, if you have pollution, then you have a third factor which damages further the attempt to keep the capital stock at a certain level, so the system converge in destroying the system, which is something that you have surely experienced in your life. The fact is, when things start going bad, they go bad fast. It's we have several examples, like this is not Feta, but Metas. You know, Meta is the new name of Facebook, and you see these people lost I don't know how many $1 billion in a few weeks. It's remarkable. The latest example of a Seneca collapse, you see, the FTX disaster. In a few days, these people disappeared. Seneca collapse, that disappears. That's very typical. And again, fishing. Fishing had been relatively constant for several decades, even before the war, growing slowly. Then somebody started saying we can improve. And then they went into overexploitation, and then the curve raised up, went up nicely. People say, oh, I was so happy we were catching so much sturgeon and producing so much caviar, and then bang, and then it went down. Another example of Seneca effect, which was the result of several factors collaborating with each other. Depletion and pollution together, bad government management, which is bureaucracy, is a typical negative factor in this kind of systems. Many examples. And population of Ukraine, just because Ukraine is fashionable right now, Ukraine went up until the collapse of the Soviet Union in 1991, and then down you go. It's typical. All the countries of the former Soviet Union went through this kind of curves, which are the results of a series of factors, because the population have been growing up to a certain level, then series of lack of good food, bad health care system, stress, lack of work, a lot of too much vodka and these kind of things, and then you go down faster than you grow. This is another typical example of the Seneca effect. Few more slides. Something about the Seneca rebound, because depends on the scale you consider. Now, even the limits to growth had a scale of 100 years. In 100 years, the global system, if things are to go as it was expected, the system will not recover. Once we run out of oil will reform, as you know, if you know about a little about geology, but in a few million years, we'll have oil again, probably, but over the time scale, as I said, of a few hundred years, no. But rebounds do occur. Also, they are a typical feature of biological system. They are a typical feature of this kind of complex systems. Just as an example, you take a look, imagine Europe at the end of the 14th century, after the Crusades, the Great Famine, and the Black Death. It was a disaster. Europe was a depopulated continent, poorly managed, poorly governed, running out of resources. People were depressed and pessimistic, a little bit like now, I think. Then you see Europe rebounded, and then it was the age of explorations. Because you recognize probably the monument which is in Lisbon to the explorers. They did a lot of damage, these people. I'm not saying that they were good people, not at all, but that's another story. But Europe had at least 2 collapses and 2 rebounds during the past millennium, which means that we can rebound. And an example of the Seneca rebound It's fantastic. This is the most amazing graph of the 21st century. You remember what I was telling you about Hubbard, the Hubbard curve, and the Hubbard curve was okay, was fine. He made a good prediction of when the peak was and the decline up to about 2005 was okay. Then something happened, bang, it goes up again. Fantastic, unbelievable. Nobody before 2008, you remember the big financial crisis of 2008. Before 2008, everybody was saying, well, the production of oil in the United States will keep going down slowly as it should do because of depletion coupled with financial factors, and it will keep going. There's nothing to do it. All geologists in the world were agreed on that. You would ask them, how about this new oil, fracking and shale oil and tight oil? I will tell you, no, it's not possible, too expensive. And they were right in a sense, but costs are not the only element of this. It's a human element. If humans scared of the great crisis of 2008, humans who have some power, humans who can influence the financial world, they say, okay, now we have a problem with oil. We don't care about cost. We need oil essentially for military purposes, because this is one of the main points of oil, is that its main factor of wars. It causes wars. You makes it possible to people to fight wars, and you know this. And so they said, we throw a lot of money into extracting oil out of shales, special geological thing, find some way of doing it. We don't care about the cost, extract it, and it can be done. You see, it is not a good thing, but it shows you what can be done when you really want to do something. Models are based on thermodynamics. The human mind sometimes, occasionally, can go against thermodynamics for a while. We need to think, if we want to change the system, if we want to avoid the Seneca collapse, if we want to move into something which is better future, we don't have to push the same thing all the time. This is something that Donella Meadows, there's not a name here, but Donella Meadows was one of the authors of the first edition of The Limits to Growth. And she was a bright mind, a very brilliant mind who could see beyond the models, because this is the trick of modeling. Is you can make all the models you want, but you have to see beyond. The model is something that could happen, but no, it will or will not, depends on many things that are not in the model and cannot stay in the model. And so you have to think in terms of leverage points. A little change can make enormous changes in the system. Just takes very little. There are these leverage points that if you know how to pull the levers, then you can do things you cannot even imagine, like indeed, like this. That was completely beyond imagination just 10 years ago. 10 years ago, people would say, ah, that's impossible, and it was possible, just like what's happening now. Another big, enormous, fantastic, unbelievable change, because people say, well, okay, the world can only live with oil. Without oil, there cannot be civilization. 1 second. Well, wait a moment. Why? Because it is too expensive. Renewable energy is too expensive. We can never use it. We'll never be able to replace oil. Yes, it was true in 2010. You see, the cost of solar photovoltaic energy was about double that of natural gas. Shift forward 10 years, things are enormously changed. Enormously. Now, the cost of the new renewables, wind and solar panels, it's less expensive, but that much better than this, because you know that with the current crisis, the cost of natural gas has gone up a factor of 10. So you have a new source of energy which costs to you 1/10 of the previous sources. It's a revolution. It is a leverage point that changes everything, and it is changing. You see this? Nuclear went through a typical curve, one of those curves that systems do, but the nuclear didn't go down because the nuclear have a long survival times. Once you build a nuclear plant, it can survive for about 40, 50, 60 years. Then it is a big problem, but let's not discuss that right now. 2020, 21, they alone surpassed nuclear. And you see how fast they're growing. This is another Seneca rebound. It is possible if you look beyond the models. You have to expect this kind of things. And it is the best thing that could have happened to us during the past decades. Change the world, it's changing everything. And we have a chance to survive, which is already something good. Don't you think so? I hope you think so, because some revolutions takes really a short time. You see here, 1900, 1913, 13 years before were all horse carts. 13 years later were all petroleum cars. And so things do change. So to conclude, we have some rules that you may consider, but I think if you follow the seminar, you understand what I mean. Always remember Seneca. The way to ruin is rapid. The fact that something is going well should make you think about the possibility that it is going too well. And that means going beyond the model. You go through the model, you see what is beyond. And you can, within limits, you can fight the Seneca cliff. You can, but you have to think before it happens. You can read more of this in this blogs of mine. And I would like to thank the Club of Rome, and I forgot to write the name of Ilaria Perissi, who helped me a lot in this kind of studies we have been doing. And last thing that I wanted to show you, you can read more about this object on this book, of which, as Roberto said, I'm an editor together with Carlos Alvarez Pereira. And this is a long multi-author discussion of what was the 1972 study. What was its relevance for that time for us, why it was not understood, how can understand it now. And okay, that's if you want to know more, there's probably more than you want to know. You really want to know in this book. So thank you very much. And also you can, if you like, I can write me, I send you a Seneca t-shirt.
Thank you very much, Ugo. Is there any question from the room?
My name is Jonah Messinger. I'm a physics PhD student here at Cambridge. I guess my sort of like initial reaction is that like, I usually don't like the invocation of physics or science, particularly like physical laws in the domain of social science, because there's, I think, often a confusion of empirical analysis and actual underlying physical laws. So you show this sort of like Gaussian, like bell-shaped curve, and as if it's sort of like a physical inherent law in, say, that manifests in, say, coal production in the UK or peak oil. I guess the point I'm trying to make is that's actually not the dynamics at play. It's instead that there's a peak in demand because we find a better energy source like natural gas or nuclear or solar and wind. And so I guess my question for you is sort of why sort of using, and I think it's misplaced, sort of like these physical laws as a crutch for these arguments, when instead I think that it gets the dynamics actually completely wrong.
Okay, I'm not sure what is your question. Is yours a question or a statement? I understand your point. I was kidding. You don't believe it. That's perfectly fine. The reason I find these models fascinating is because they work. Very simple. And if they didn't work, of course, I wouldn't lose my time into so much work into making these kind of models. Then if you think there are other more important factors, I agree with you. There are other factors that we don't stay in the model. Just like I said, when I showed you the peak oil, the Hubbard, you see, this curve you can see here. It's you like this. You see, this is not in the physics of the system. So this is beyond the physics. You have to be careful. And I think you're making an interesting point. You don't have to trust physics too much, because There is human factors, and in the book we discussed this a little bit. It is a very difficult point because you can once you start thinking in terms of human psychology, then anything can happen. People may decide, oh, we don't want oil anymore, so we would have the opposite. You could have had completely different way to go, depending on people's decisions. But let me repeat, in general, very often the model works. And when it doesn't work, you understand that there are very special, very specific, very particular, understandable reasons why it does not work. It tells you at least a baseline on which you can understand what's going on.
Sometimes like, human ingenuity or something can go beyond physics, but that's obviously not what's going on, right? For example, for big oil, fracking breaks that model, but it's not physics.
I'm not sure I can follow you, but as you said, the model is falsified by fracking, but the model remains very valid. If people had not decided to spend a lot of money and lose a lot of money, because fracking has not provided revenues for anyone. Fracking is a typical military decision by the United States, because they need oil to keep the empire, because it's the way you call it, the empire going. And then you don't care about money. The system, what you can call this kind of approach, and it's a term that I didn't use, but you can use it, econophysics or biophysical economics. As long as the physics of the system drives the economics of the system, you have a predictable behavior. But when you start saying, well, let's go to war, then wars are not predictable by the model. I see. Because wars are a failure of the model, of the network. The model works essentially, as I was saying, it's because there is a network, a tight network. Once you decide to start a war, you break the network in two, and then everything changes. But it's another story.
Thank you.
Okay, can I just add something on this point exactly, just to give a bit of background as well, because the story of limits of growth changed over 50 years as well. So just if you see Earth for all is a different book, right? So the limits of growth was the world collapsing. Earth for all is not collapsing, so the world doesn't collapse. So these things of ending minerals for people like Jorgen Randers is not happening in the next 20, 30, 40 years. And that's the reason why, because the expectation is that somehow the economy will end up adapting itself, extracting more minerals, making things to grow. So you can agree or not with that assumption. Again, that's a matter of having a conversation. However, the big points that came from limits of growth, it was, let's say, the scary bits that these people used to be scared about in 1970. It was not really hitting the mineral issue, hitting something else. They were all aware that they were imprecise, unpredictable, you cannot really say that. So they were a bit also unsure of themselves, but they were very scared about exponential growth. I mean, that's very scary. It sounds incredible, but if you take this piece of paper and I fold it 42 times on itself, it goes 440,000 kilometers. It's scary. I mean, if you think about that, that's why they were scared about the population thing. They were scared about the industrial capital growth was going exponentially. So at some point they will overshoot the limits of the planet, no matter whatever limits we remove. So that was their concern at the time, at the end of the day. Again, the only way to avoid that, if we grow fast, but less fast than now, we build up the bridge below that. So we managed to find the resources below, we managed to remove pollution, we managed to stop having the population, which will impact somehow the environmental issues. So in fact, the exponential growth problem is, you can say all these models were wrong, but that concept still remains true. And if we grow so fast and we overshoot the limit of the planet, we end up in troubles, pretty much. And that's when, that curve of the US in 1970 was a big trouble for the US. They stopped having the monetary fund, they used to have the gold standard at the time. They changed that because they couldn't employ people anymore because they didn't have oil. And so they started like moving into this sort of foreign exchange market, things like that. they managed, at some point, they managed to go so deep in the ground to extract more resources, which is fine. We have a lot of resources around the world, but the big problem again is that you end up destroying the climate issue. So the planetary boundaries concept again is still true. You cannot say that very precisely, but still we end up in this trouble because you cannot measure it and you cannot manage it, and we have to find anyway a way. I don't know if this somehow covers a little bit of your point as well. Thank you. And would you feel like, please?
Just a real quick one. So I'm Sebastian, I'm studying sustainable finance. And just sort of observation on the fracking point, I think a very, very reasonable point. To me, it's the measurement in what is being measured is obviously an issue with those graphs, which is why they don't make any, they obviously look extremely silly. He calls a very silly concept on the basis that it's based on assumptions about technology, specifically interest rates. It's just a couple of things I wanted to add. It's not the case that there wasn't substantial revenue opportunity in fracking. The profitability was minimal for the last 10 years. And it was obviously based not off US government policy specifically, but very low interest rates, which allowed companies like Chesapeake and the big fracking operations, XOM, which was bought by Exxon, to continue to operate on negative margins. It wasn't necessarily a US government a planning position. It was purely really a financial and technology.
Yeah, of course. Okay, so thank you very much, guys. I start by asking question from the chat, Ugo. Just to Aaron Paes is asking what is the difference between limits to growth and Earth for all model. So one collapse, what does not collapse? What's the right one?
It is not the Earth for all doesn't say collapse. It is. Doesn't mean that it will not collapse. Earth for all is based on some assumptions, which says if we do a certain number of things, we follow a certain number of paths. But if you look at the book, if you read the book, you see that some of these paths lead to collapse. No problem about that. It is always the same thing. I say, I was convinced up to a few years ago, I was convinced that we would see a collapse soon, and we still are on track for that. But the new developments in renewable energy, and now we can hope that the collapse, if not avoided, can at least be mitigated. So you have to change all the time. A model is not a predicting tool. It's not there to predict. It's not a crystal ball that you look into and you predict the future. The model explains to you the future. The model is there to tell you, like this, where I say, what's happening here? Why didn't you predict this bump up? Because predictions are not the business of the model. You cannot do that. The future is always complicated. They're always surprising. You never know what people, I mean, think of your own cat. The little beast will surprise you often, right? So you cannot predict the behavior of your cat, to say nothing about your wife or your husband. So think about this, but what it tells you, because otherwise you don't understand anything here. If you don't have a model, you cannot understand why you have this behavior, what's happening. Just like before there was this big change, I was speaking with economists, and they say, how do you explain this peak? I said, it's because the United States government ordered to turn off the taps. That is not, it makes no sense. There's no such possibility for the United States government. They could not do it if they had wanted to, and they for sure they didn't want to do this. You can understand this because you know the dynamics of the system, because you have a biophysical view of the system. Then if you have this biophysical system, you can see at this bump and say, okay, that means that something has changed inside the system. And then the parameters are changed, and then something different happens. You go to look at the Russian case. The Russian case is very similar. It goes like this. Now, Russia. Why that? Why did you have to pick? Because this was the Soviet Union. This was Russia. Soviet Union had an economic system which was completely different. They had expenses which did not occur for Russia, or the Russian Federation more exactly. And so that's as soon as when the Soviet Union collapsed, they went down a nice Seneca cliff. And then changing the parameter of the system, use less expensive, less military expensive, at least up to now. I don't say anything about what's happening now, but then they could restart a Seneca rebound. And the beauty of this thing is that it gives you an interpretation. You can understand why the system does certain things. Now, what is going to happen to Russian production in the near future? I don't know. I would not launch myself in trying to tell you whether they are going to collapse at the beginning of the war. People are now with the sanction that will collapse in one week. This is not happening, and because the system is complex, but at least you have a chance.
Thank you, Ugo. So there's another question about the renewable energy transition. And the question is, how many decades are left to make the transition to happen, assuming climate change will not kill us by 2070, for example, that many countries are picking 2070 as a target. And also, if I can add my question on top of this, just because I know you are familiar with the field. So, for example, in the context of the energy transition, we're expecting to have green growth, things like that, but this will end up putting a lot of weight on the mineral sector. So, everything, if you want to electrify the entire world, we need to take a lot of minerals to make things that will allow us to make the electrification possible. So what's your view on that as well?
Yes, right. I wrote an entire book on this subject. So I think I have some idea, but whenever you make predictions, you're sure to be wrong. That's one of the things that we can say with some certainty. But the point is, so if you ask me, just let me make you an example how technology and mineral resources connect with each other. Everybody's talking about hydrogen and fuel cells, okay? Now, fuel cells, the current technology, uses expensive minerals and rare minerals to function. You need platinum for fuel cells. Platinum, typically also iridium, but mainly platinum. So you make a simple calculation. You want to replace the current hydrocarbon-based energy system with hydrogen and fuel cells. You cannot do it because you just don't have enough platinum. No way. We are orders of magnitude away from that. And that has to be taken into account. You have to, by all means, because fuel cells are a known technology. It has been working in a certain way for 50 years. You use this technology for fuel cells. There are other technologies which don't use noble metals, but they are not standard. When you deal with silicon, photovoltaic panels, you deal with silicon. Silicon is the main element, the main metal in the Earth's crust. So you don't have the same problem. You cannot say, well, we run out of silicon, because solar panels are made mainly by silicon with some traces of phosphorus and indium traces. So the only problem we have with solar panels now is some silver they use as a back plate, but you can make, it's not fundamental. You can make panels, PV cells without silver. So that's a completely different story. You can make a certain system is not resource limited. Other systems are. Now you go to nuclear energy, you are uranium limited because there is just so much uranium. So you have to take that into account. You go to lithium batteries, that's a very complicated story. There is a limit, but right now we cannot see it exactly. It's somewhere there is a limit for sure, but we are not there yet. We can keep making batteries for quite a long time. And then we can switch. The beauty of batteries, I was trained as a chemist. Batteries are a fantastic technology. You can enjoy yourself making different kinds in many ways. So it has to be taken into account, but you have to be careful in what you do, because some people say that we cannot do anything because there is a mineral limitation. No, we can do a lot of things if we use minerals which are abundant, and of course we recycle them. And if we do that, we can keep the technology, the industrial technology going. Some caution, because everything changed. Everybody, when I say this, everybody tells me, oh, you want to keep the world just the way it is and no changes. No, if you change the energy technology, the system will completely change. But then it is difficult to predict it. And as I said at the beginning, prediction is very difficult, especially when it has to do with the future.
Thank you very much, Ugo. Also, just as a comment, I just wanted to say that also Professor David Lane is participating from the chat. So thank you, Professor Lane. And also one thing that Professor Lane says is that the model in practice is not falsified in the moment in which the data don't agree with that model. The only reality is that by changing the parameter that was used to run the model in the 1970s, that basically falsifies the scenario built with that model. But in practice, the truth of the model still lies, even though we still didn't reach that sort of crazy limits of the world as we expect. It's very simple to understand that is finishing the resource of the planet is like finishing a glass of beer. You know, the moment you don't have it anymore, you just don't drink anymore. And that's pretty much the concept. It's like having a parameter telling you how much beer you can drink. So pretty much, I think that's the idea. There is a question from Frederick Guarino, and Ugo is linked back to the population. And when you said about the population of Ukraine, there was somebody asking for the population of Japan, which is also another case of the growing population. What's your take on it?
About Japan, I discussed that in my book, The Seneca Effect, and it is a very interesting case because they could maintain a stable population, about 20 million, if I remember correctly, for the whole period of the Tokugawa shogunate, which it's an interesting case, a modern case of stability. It's something that I discussed in the book, whether we can learn something from Japan, from the Tokugawa Japan. And we know a lot because it's close to us. The Tokugawa government collapsed in the early 19th century. So it's close to us, so we can learn. And it was a very tight world. It was not rich. The people were poor, by all means, very poor. There was a birth control system, which is, that's a little bit difficult to understand exactly how it was obtained. You know that there was this, you can read about the story of the Mabiki. Mabiki means hiki means take away, and ma means a plant or something, means it is understood as infanticide. But there's not to be exaggerated. Infanticides happens in all society in the world. There were no reason to think that the Japanese were more more killing babies more than anybody else. It existed, but in reality there was plenty of contraceptive ways to avoid overpopulation. In any case, occasionally you had famines and some people died, but it was stable. Actually, it was never those giant famines that killed millions of people in other countries of the world. And so it was, I think it was an interesting place to live, Japan, during the Shogun time. It was art, literature, mathematics, and architecture and religion. It was a very vital period. So I think it is possible to maintain stability without losing civilization, because the Japanese civilization was very advanced even before, perhaps more advanced than now. You could argue that. And if we need to keep, anyway, we need energy. The Japanese were still linked to agriculture, and they had this big advantage that Japan is a very rainy place, so they didn't have the big problem of drought that we have. And I think the beauty of renewable technologies like photovoltaics is that they naturally tend to stabilize, because there is so much land that you can use. So as you cover, and then eventually you have to stop. You cannot panel the whole planet. It makes no sense. So you have to stop. And so I do think that if we move to renewables, then we are naturally moving to a stable world without the need of doing strange things or killing people or whatever. And this is one conclusion. If you read the Earth for All, you will see that they describe something similar, although they don't discuss Japan.
Thank you, Ugo. There's another question from Joya. She's asking about an example of a stable system you can learn from, maybe we can aim for.
An example, there are not been so many in human history. That's an interesting question, because we have Japan, as I was mentioning. We may have the ancient civilization of the Middle East, like the Sumerian, these people, but that's so remote in time. It is difficult to say whether we can really learn something from such ancient civilization. Then very few societies have been stable. For instance, as I was showing to you, Europe didn't manage to have a stable system. They went up and down, and then we don't know. We're still growing a lot, and we don't know if we will be able to maintain the current level of population. And let's say that it is typical of these models now. They tell you that all systems have a tendency to stabilize as long as there is a renewable supply of energy. The system moves because it disperses energy. If it uses up all the energy, then it dies. It happens. But if you have a constant supply of energy, like the sun, for instance, then the system will tend to adapt. It takes time. Also for Japan, the Tokugawa stability was the result of a period of big wars. And then eventually they stopped because it's useless. They had to stop. But they probably, before the wars went in overshoot, overused land, then there was not sufficient energy or food. That was the main energy at the time for everybody. So they had to go to war. And then eventually they found a stability. And I think we will do the same, although clearly we are not there yet.
Okay, so thank you very much. How realistic do you think it will be a society that shifts from growth to a sustainable way of living via the growth?
Now, this is an interesting question, because I can tell you that back in the 70s, when this study, the original study was being discussed, there was this kind of debate: degrowth, growth, or zero growth. What does it mean? That it's a very nuanced question, because what is zero growth? You can read, and there was a big debate with Aurelio Peccei, who was the founder of the Club of Rome, and somebody asked him, do you support zero growth because of what you wrote? And I said, not at all, but no way, I don't support zero growth. Because if you have zero, if you freeze the system, then inequality remains the same. It means the poor remain poor, the rich remain rich. This is a big problem that I didn't say anything here, but you can make models of that too. The problem of inequality. And that's one of the main points of the Earth for All, which is another subject. Earth for All discuss equity, to establish a certain degree of equity, not necessarily equality. Equality is it's very difficult. How do you do that? But to make sure that nobody is left out of the prosperity that society can create. Very simple. And this is a point which I'm afraid that the modern people who are promoting degrowth, they don't normally consider that. Who is going to degrow? I'm very much inspired by Roberto Peccei at this time. Not Roberto, but the son of Aurelio. Aurelio was the founder. Who is going to degrow? question is not often asked. But it is asked. If you ask to some people from Africa and say, "You want me to degrow? No, you degrow." And so this is but in practice, what happens is that the poor degrow before the rich, and that's a little bit of a problem, as you may imagine.
Okay, thank you, Ugo. And then there is a question from Noé Martinez. The question is about the new features in the model about technology can help better predict.
Absolutely, absolutely, yes. That's one of the many fascinating points of this, because you move away from the mechanics of the model. The model telling you if you're stupid, that's what happens. And since it happens so fast, it means that humans are not so smart as they think they are. But if you are smart, really, then you change. And that's what the models start telling you. It's a new, fantastic, fascinating thing that you can explore, because Donella Meadows explored it. I'll show you a slide about the change of paradigm. First, most important, you change paradigm first, and you can change things, or just go touch the critical points of the system and you can change a lot of things, but we are still learning. I think the future here is the mixing of artificial intelligence. We have to mix artificial intelligence with this kind of models, because once you start using artificial intelligence, you can explore possibilities that the mechanistic, if you prefer, model cannot analyze, and which is the weak point, because correctly said, we are not bound by the models. The models tell us mostly what we cannot do, but there is a lot that we can do, and it is not in the model.
Okay, thank you very much, Ugo. Is there any other question from the ground? Yes, please.
Hi, I'm Lucy Goodman from the Department of Geography, and my question is kind of, I guess, related to my interest, which is around renewable energy and debates and developments. You've talked a lot so far in response to a lot of the chat and also the questions from the floor about the shape of the Seneca curve. My question to you is to reflect a bit more about the x-axis, the timeline. How long can that period be for it still to be a Seneca curve, for it to actually be following the shape and still be describing the phenomenon that you've been discussing? Related to one of the questions from the chat, which was about how many decades there were to the renewable energy transition, and kind of if you can reflect on this, and also how long have we got left to make a change? That's the kind of thrust of my question.
That's a very good question. Very good. I wish I could answer to you, because we would like to predict the future, but we cannot. There is something that very basic. I mean, I try to understand how these models could really predict the future. No, they cannot. And the time scale, they can tell you some big change may happen, as you said, the Seneca cliff, but when, how fast, up to how long, how far down we are going to go. It's very difficult. See, I could tell you about the ultimate collapse, which is the collapse of the Earth's ecosystem, which could happen. It's the climate science arrived to a similar idea when they discuss about tipping points. I guess you know what is a tipping point, right? You know, tipping points, for instance, methane hydrates. Methane hydrates is a positive feedback effect that you evaporate some methane hydrates. The hydrates heat the atmosphere, you evaporate more, and then you have what is called the Venus effect, that the Earth system goes down to the curve to a condition in which you have about 600 degrees temperature, 600 Celsius, maybe, and never mind, 600, too much for us humans. This is the total collapse of the Earth's ecosystem, due to a tipping point, which is essentially the same thing as the Seneca effect, because you have something that starts pulling down the system and does that in a feedback driven effect. Now, you ask the climate scientists, when is that going to happen? Is it going to happen? Probably yes, if we don't stop doing a certain thing, but when? And that's, you can ask any climate scientist, not possible to know. We don't know because it's too fast. The parameters, the system reacts non-linearly to small changes of parameters, so you cannot predict it. You could go to hell, essentially, Venus, in maybe in 100 years or less, maybe in a few decades. We know nobody, or maybe thousands of years, tens of thousands of years. And the only thing you have, be prepared. And that's one of the main points of the urgency of the effort, of the emphasis on climate change, which is correct. It's a correct point. The disaster could be gigantic, be beyond anything we can imagine, but we cannot frame it in a time scale. And you know, you can ask Professor Bardi, say I don't know, because but if you ask to climatologists, thousands of climatologists exploring this field in detail for decades, but they cannot predict it. Ask them. And so it is a limitation of our brain, or perhaps it's a limitation which is inside the way, the fabric of the universe. That to us, it is not given to predict the future.
Thank you.
Thank you very much, Professor Bardi. I think now we really need to close. It's 6 p.m. and just want to thank everybody for joining, everybody from the chat. I think the discussion was very much interesting. Thank you, Professor Bardi. Thank you also, Professor David Lane. That's handled the chat much better than I could on my own. And maybe I can cite his last comments when he says the very deep words, models help us argue. So they're not meant to be, you know, the prediction. Rather than merely disagreeing, we can have more sensible discussions about the parameters and assumptions that we are using. So in practice, it supports a discussion, then we can talk and make the world we want. That's, I think, one of the main objectives of building a model. So if you build a model, it creates so much discussion, that was a successful one. Next week, we have Mountfela, she's co-president of Double Wrong. Please come along, it will be very exciting. And I mean, that will be a very big discussion, a bit, I think, separate from the modeling, a bit more into the humanity, what we can do in practice. So if you are interested, I think that will be a very interesting talk as well. So again, thank you very much, Professor Ugo Bardi, for your time. And again, thank you very much. Bye all. See you next Monday. Bye.
Okay, bye everybody. Thank you for listening. Bye.